right, welcome to the groundwater lecture. And that's what I'm so happy about in this picture. There's rock back here, and you can see how it's a little darker there. That's because there's actually water coming out of the ground there. So it's going from being groundwater to being surface water at a little spring off in Colorado. Now, groundwater is quite important to us because we use it all the time. It's used as a source of drinking water. In fact, many cities have wells, and they take water out of the ground and provide it to their residents. And if you have a well on your property, well, you're using groundwater for your water supply. So we use it for drinking water, we use it for irrigation of crops, we use it for livestock, and making sure they have enough to drink. And industry uses it quite a bit as well. Water is used in a number of industrial processes for making things, as well as a coolant for certain things. So some important concepts to keep in mind when we're looking at groundwater is oftentimes people picture groundwater as in, like, it's just this pool of water sitting underground, and it's not. It is actually flowing. Groundwater is always moving, so it's more like this river underground that's slowly moving through the rocks. And the movement depends on the characteristics of the rock. In fact, two very important characteristics: porosity and permeability. Porosity is the open space in the rock, and permeability is how those spaces are interconnected so water can flow through the rock. And what we're looking at right here, this is something called a thin section. It's where we cut a rock so it's really, really thin, and then we look at it under a microscope. And each one of these little areas right here is a grain of sand. And the blue area is the porosity. So this rock would have high porosity, right? There's a lot of blue, so this kind of rock would be able to hold a lot of water, and the water would be able to flow through there. So good porosity and good permeability. In this case, again, these different colored areas are grains of sand. But one thing you don't see in there is much porosity, right? There's not a lot of open space, and we don't see any blue. So this would be low porosity and low permeability. Water would not be able to pass through that. So a rock that has this good porosity and permeability is considered an aquifer. That's rock or sediment that freely holds and transmits water. And the opposite of that is going to be an aquitard. This is something going to be with low permeability, so it's rock or sediment that actually restricts, it hinders the flow of water. Now let's look at a typical aquifer. Now I have that drawn right here. Here's our typical aquifer. First of all, we have Earth's surface right there, and then here is the water table. The water table is a surface that separates saturated rock or sediment from unsaturated. We call this area that's not filled with water the vadose zone. Now that's the vadose zone. Then under the water table is the saturated zone. So that rock is 100% completely filled with water. Notice the way I have this water table drawn. It's usually a subdued mirror of the surface topography. So if we have a hill on the surface, we have a hill in the water table. And any place we have surface water, like a little stream or a pond or something like that, any place that we have surface water is a place the water table intersects Earth's surface. And so there's our typical, very basic aquifer that we would have. Now this aquifer would be considered an unconfined aquifer. The aquifer is only overlain by permeable material. That means if it rains over here, some of that water is going to infiltrate, it's going to soak into the ground, and it's going to flow downwards towards the water table. And same thing would happen over here. There's no barriers between the water table and the surface. And one thing I need to add to that, remember I said water flows underground? Just like on the surface, it flows from higher elevations to lower elevations. If the water table is higher over here, it's going to be flowing in this direction, right? From high to low, so the water's moving. Now that's a typical unconfined aquifer. We also have something called a perched water table. So imagine if we had a layer of rock or sediment here, maybe it's shale. Shale tends to be very impermeable. It does not allow water to flow through it. And then we have a storm. It's a very low cloud, right? Water infiltrates downwards, and it's going to get stuck right up here above that impermeable layer, right? It cannot go down any farther. That is called a perched water table. It's this small area of saturated sediment or rock above the main water table, above the main regional aquifer. Now, a third type of aquifer that you might have or might see is something known as a artesian aquifer. And to have an artesian aquifer, we need a very specific setup to occur. So in an artesian aquifer, it's where water is under pressure and it rises above where it's first encountered. So first of all, there's my land surface, right? I have a hill or mountains over here, flat area over here. My aquifer is going to be tilted. So this is my aquifer filled with permeable, porous rock. Surrounding that permeable, porous rock is going to be something impermeable. And impermeable rocks are often igneous rocks or sediments like shale is often impermeable. So that means if that's all impermeable, water that gets into this aquifer is kind of stuck there. So this is an area we call the recharge zone because that's the only area where water can enter this aquifer. Can't enter it down here because that impermeable rock separates the aquifer from the surface. So what's going to happen, water will infiltrate here, it'll flow downwards as far as it can go, and then it gets stuck there because it's surrounded by impermeable material. Over time, the aquifer might fill up all the way to here. That means all of this rock is filled with water. All right? So what then happens to make this artesian? This is under pressure. The water's all the way up here. This sets up something called a potentiometric surface. My arms aren't long enough to reach there. All right, so that's a potentiometric surface, fancy name for a pressure surface. So if I drill a well here into that aquifer, I run into water there. But the water's above here, it's pushing down on it. That's the pressure I'm talking about. So this water is actually going to rise all the way up to the potentiometric surface. That's an artesian aquifer. The water is under pressure and it rises above where we first encounter it. In fact, parts of Texas have artesian aquifers. There's an aquifer known as the Ogallala Aquifer that is underneath parts of Nebraska and Kansas. And that's also a very famous artesian aquifer where people would, back when they settled the Great Plains, drill into the ground, hit this water, and it would come shooting out of the ground because it was under pressure in that artesian aquifer. Now, there are a number of problems when you use a lot of groundwater. And one of these problems is the cone of depression. Sort of sounds like that thing my dog wears when he comes back from the vet. But actually, the cone of depression is a groundwater problem. So what we have Earth's surface right here. And let's say we have a well into the aquifer. So let me put on, here's the water table. The water table is always drawn with a little triangle, just to let people know that's the water table and not a layer of rock. So there's my well. I'm extracting a whole lot of water from that. And I'm extracting more water and extracting the water faster than it can flow back into place. So what happens around that well, the water table goes down. So all of this area that's right there, all of this that used to be filled with water is now dry surrounding the well. So that's all dry because we're taking out the water faster than it can be replaced. Now, the good news about the cone of depression is that it's reversible. If you start conserving water and not extracting it as fast, it'll flow back into that location, no harm done. There are, however, some groundwater problems that occur that are irreversible. And one of these is subsidence. So if we continue to remove groundwater, what can happen is sediments can compact. So originally you have these sediments sitting like this, and in between them there's this water. And just like I know when we went over like metamorphic rocks and things, we said there's the weight of the rock is called lithostatic pressure. There's also this hydrostatic pressure. There's this, the water is a liquid that cannot be compressed, so it kind of keeps those sediment grains from squishing closer together. But if we remove the water from there, we lose this pore fluid pressure. We lose the force of the water keeping the sediment grains apart so they can compact closer together, like what they've done right there. They compact closer together, and now imagine hundreds of feet of stuff squishing closer together. You get subsidence at the surface. Subsidence is where the whole surface of the ground lowers in elevation. And one of the best places to see this is off in the San Joaquin Valley in California. If you had gone there in 1925, the land would have been all the way up here. But in the course of about 50 years, they withdrew so much groundwater for irrigation in this area, those sediments compacted, and the elevation by 1977 was all the way down there. That's 30 feet of subsidence that occurred because of withdrawing this groundwater. This is irreversible. It's not like you can pump water back in there and reinflate this. Once that happens, that's it. All of that porosity, basically when it's subsided, that just squished the porosity out of the rock, all of that is now gone, and this aquifer will never be able to hold as much water as it once did. Now, there are other sources of contamination, or other problems with groundwater, and another is contamination. You can get chemicals or substances in the groundwater that you just don't want there. Common places where we can get these are like industrial complexes can have spills, and anything that's spilled on the surface, some of that can seep into the ground and join the groundwater. Landfills can sometimes create groundwater contamination. Gas stations, you know, the gasoline's kept in tanks underground, and if those have a leak in them, that's going to contaminate the surrounding groundwater. Septic systems if they're not properly maintained, but there's lots of sources of groundwater contamination. And one of the big problems, like I said earlier, is water then moves, so that contamination can get carried all over the place underground. All right, karst topography is another interesting thing that occurs because of groundwater. It's both a hazard and it also creates some very beautiful landscapes. Karst topography is a landscape shaped by the solution activity of groundwater. So the solution activity means the groundwater is dissolving away the rock. And this can only occur then in soluble rocks, rocks that can be dissolved. And this is pretty much limestone and dolomite, although you will see some of this also in places where you have halite underground and gypsum underground. So typical things that you're going to see in an area of karst topography, you're going to see caves, like Mammoth Cave here. This was all limestone once upon a time, and the groundwater flowed along little cracks and little openings in that limestone and dissolved more and more and more of that limestone away, creating the cave. This is another cave. This one's in Wisconsin, but all of this space that's open now was once rock, and water dissolved that rock away. Another thing we see in karst topography are things called disappearing streams. They're exactly what they sound like. They're a stream. Now this is a topographic map, and this little line right here, the 3 dots and the dash, that represents a stream. And a disappearing stream shows up, it flows for a very short distance, and then it disappears. So what happens, it pops out of a cave here, flows over the surface, and then it disappears underground into another cave. And that's what we're seeing right here. There's a cave system there, and this is one of these disappearing streams that is suddenly appearing on the surface. Now, karst topography, one of the hazards associated with it is sinkholes. This is a sinkhole. A sinkhole will develop when the roof of a cave gets so thin it can't support itself anymore and it collapses. So basically, this used to be all underground and there was a covering here of rock, but more and more of that rock got dissolved away until it no longer was strong enough to support itself and it collapsed inward. Same thing happened here. This is the Winter Park sinkhole in Florida. Basically, this thing collapsed overnight. And to give you an idea of the size of it, that's a swimming pool. This is a 4-lane road. That is a pickup truck with a camper top on it. If you feel like watching a sinkhole opening up, go to YouTube and just in the search bar type in Corvette Museum sinkhole and you'll be able to see one occurring in real time. Now, sinkholes are not isolated features because they occur in bedrock. You might have a whole region that's underlain by this soluble bedrock. And so you're going to get a whole region with lots and lots of sinkholes. And that's what we're seeing right here. All of these little dark sort of round lakes, all of those are sinkholes. This is part of Florida. And so this is showing you where you've had one sinkhole, you're very likely to get another. All right, I'm going to finish off by just taking a quick look at some interesting things like hot springs and geysers. Hot springs and geysers are typical of volcanic areas where the magma is close to Earth's surface, so it is actually heating the water of the aquifer. And so this is a hot spring, comes out of the ground, not quite at boiling, but it is definitely some very warm water coming out of the ground. This is a geyser. What happens to create the geyser, the water underground is actually superheated to the point where it's going to end up getting under pressure and exploding out of the ground. That's Castle Geyser in Yellowstone. And I said I like whitewater rafting. This time you can tell, that's me. This is on the Taos Box up in New Mexico on the Rio Grande River. So anyway, there we go.